that may give us some issues with our domains and ranges. Okay, so we did like examples 3 and 4 there yesterday. We did these 2 examples. We identify the domain and range, right? Find the domain is your what values? X's. Find the range is your Y's. Okay? So I just want to create real quick a function that I can kind of mess around with. So don't write this down, but just kind of watch. All right, so just looking at this graph here, okay? We're going to look at the equation. That'd be the equation of the curve. Okay, we don't really need to really be interested too much in that, but this is the curve that I'm interested in discussing with you right now. Okay, and once that finishes, we can maybe get rid of some of that stuff and make it a little bit less cluttered up there. But my question is, let's talk about the domains and the ranges. Okay. And actually, let me do this, because I think it maybe makes more sense or is beneficial to flip this. Let's go. Let's shrink that down. All right, good enough. So let's look at that function. When I ask you the domain, okay, remember that the domain is the set of x values, the set of input values that you're allowed to plug into the equation and generate an output, get something back. Okay? If I look at this equation here, kind of think about the x values that you can plug in there. Think about any x value that you want. When you plug it in there, can you take any number on the real number line and raise it to the 4th power? You take any number on the number line and multiply it by -0.2. You take any number on the number line and raise it to the 3rd power and multiply it by 0.5. You take any number on the number line and square it. You take any number on the number line and multiply it by 0.9. You take any number on the number line and add 0.8 to it. Okay? So can I then, if I can do all those individual things, can I just add those all together? So what's that tell me? Will I ever have an x value that I can't plug in? No. Okay. I should be able to plug in any x value that I want to. Okay. Now the thing is that people struggle with seeing is, well, you're saying I can plug in any x value, but if I zoom out on this thing and I go down pretty far, it go down to like 100, or even if I go down to like 320, it looks like my x value is around like maybe, I don't know, 8 or 9 here. Does that make sense? And that's fine, but you're thinking, well, how am I going to get to like -1 million on the x-axis? Well, the way I get to -1 million on the x-axis is that I go down pretty far on my y-axis. Does that make sense? Okay. And we can prove that with the idea that, if I take f, f of like 1 here, it gives me this 1.2. It gives me that output right there where my cursor is. But if I go like f of 100, see that y value that I get? It's a very large y value, right? There's thousands place. So it's 19 million. Okay, pretty large value, right? H was, my evaluating value was 100. Okay, so when x is 100, I get down to 19 million. So that's zooming out pretty far to see that this thing does exist over an x value of 100. If I try f of 1,000 or 10,000, okay, or f of that number, okay, am I getting something back? Yeah. Okay? So because I'm getting things back for all those values, we can kind of interpret that there is no x value that I'd plug in that I wouldn't get something back. So my domain here is going to be all real numbers. Okay? So domain is all real numbers. Okay? This is a polynomial. You guys remember that that like a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 plus then dot 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 plus a sub 1 x to the first plus a sub 0. Remember hearing that phrase and writing that down a couple weeks ago? Okay. Anything of that form, anything that is polynomial, will have a domain that is negative infinity or positive infinity. You can always, and we talked about yesterday, somebody said yesterday that linear functions are always have a domain of negative infinity and positive infinity. Well, a linear function is kind of our most simplistic version of a polynomial function. Okay? Negative infinity, positive infinity is its domain. Everything else that is polynomial has a all real number domain. Is that okay? That's a fact that's going to help you do some of your homework tonight maybe a little bit more efficiently. All right, so now let's talk about our range. Our range. Where do we start when we look at our range? Do we start at the bottom and up or top down? Where? Bottom, up, right? So we'll start with like a horizontal line down here, and I'm going to slide it up to see what y values I intersect, correct? And whatever y values I intersect or y values that I'm going to list in my range, okay? So because this graph goes on forever in that direction, what would be the first y value you come across in your range? Negative infinity, right? Okay? As I move this up, what ends up being the last y value that your blue line kind of touches? About 4.9-ish. Okay? And I would include 4.9. So that's my range. Is that okay with everybody? Okay? I always go bottom up. Okay? And then that when I look at that number line, that range number line, the number to the left should be smaller or more negative, I guess, than to the number to the right. Okay, so negative infinity is more negative than 4.9, right? Okay. So those are some good things to kind of be able to do. But now I want to change this a little bit. I want to go and put in a point. Let's see if I can do this. Let's say P equals 1, comma, F of 1. Awesome. All right. So I put a point here on my curve. I want to open it up. I put that open point on my curve, and I use an x value of 1, okay? There's now a hole there. Does that make sense? I want to talk about how that impacts my domain. When I put in my line x equals r, make that dotted, let's make it red, let me hide that line. Okay, so we're doing our domain, right? Going left to right. And that thing, left to right, we're going to start at negative infinity. We're going to go up, and we get to here. And when I get to there, is that an input value? Can I get something back out? No. Okay? So in my domain, if there's a hole there, I need to tell everybody that you cannot use 1. 1 is not a x value that is available to us. Okay? Now let me show you kind of algebraically what that, if there was a hole there, that graph would look like this. It'd be the f of x function, okay? then we'd have that times, let's see here, x minus 1 divided by x minus 1. All right, so we get, this is the algebra, that blue stuff. Can't move my domain and things right now. But that blue stuff would be the algebra to produce that blue curve, okay, with a hole right here at P. Does that make sense, everybody? Okay, is the blue curve and the red curve, are they the same? Okay, about 99.99999% the same, except for at point P, right? Okay, because on F, think about this, when it's red, I can go F of 1, and I should get a number back. Let's see what that number gave me. Give you back, see where it says F of 1 right there? Okay, so it gave me 1.2 back, right? The other function was called P. When I plug in P of 1 on the blue one, P of 1, actually it's lowercase p, right? P of 1. See what spits back to me? Undefined. Because what do we have there? Look at that denominator. It's division by 0, right? When x is 1. Okay. So we have to be able to address that, and this is the algebra that would address that. Okay. Remember our domain values. It's a way of listing all the potential x values of the infinite ordered pairs that show up on this curve. The range is showing the infinite number of y values that would show up on the ordered pairs of this curve. Is it okay? So that's doing the domain. Okay, that point impacts our domain. That's fine. Can we talk about then whether that point impacts the range? I would start at negative infinity, right? I come up. The only thing that's changed from the last time we did this is that point right there, right? So that point has got a y value of 1.2. Okay? Do I need to kick 1.2 out of my range? Remember, 1.2 is going to be, if it's in my range, that means that there must be some ordered pair on my curve that has a y value of 1.2. Are there other y values up there of 1.2 on my curve? Yeah. So even though that point doesn't exist there, 1.2 is a y value for some other point, so it has to be in my range. Does that make sense, everybody? Okay. Therefore, do I need to kick it out? No. Okay. If I had, let's do this for, let's see if I can show this. I'm not sure about the notation. You're going to say x is less than 0.5. Do I want to? No. Alright. Never mind. We'll talk about maybe some more other point. So we can do that. Does that make sense? Does anybody have questions on that? Alright, let's say we do this. Let's say I put the point 1, 6 in here. Alright, so I've taken point P. It's still undefined there. It does not have a point 1, 1.2. Does that make sense? It's been removed off the graph. But I've replaced the x value of 1 with a point up there at 1, 6. Is that alright? So here's my question. Is this thing still a function? If I take my red line here, does that function pass the vertical line test? Right there would be kind of the only issue, right? Okay. But is there really a point existing right here? No. It's existing up here, right? So how many times does my red dotted line cross my graph? At 1, it crosses 1 time. So we're okay. We passed the we passed the vertical line test there. And we keep passing it everywhere else. Okay? So now let's talk about how our domain is impacted. Remember, our domain started off as negative infinity to infinity, right? Okay? When I removed point P, when we removed it and that point was not there, we had to get rid of x being 1, right? if I put that point in right there, and all of this is part of my graph, will there be an x value of 1? If I list all the ordered pairs for the red curve and that black point, will there be an x value of 1? Absolutely, right? So do I kick it out? No, I can't. I keep it, okay? So by removing that point from the curve, but replacing it somewhere else in the plane, at the same x value of 1 where I removed it, I don't have to kick out that value in my domain. Okay? If I list all the infinite ordered pairs in that graph, 1 will be an x value. Okay, some ordered pair. Now let's talk about our range, because now I think our range might get messed up a little bit, or altered. If we do our range, still going to start at negative infinity, right? Right there, we're still going to have 1.2, right? Because it's showing up here and over here. All right. Still going to go up to about 4.9, right? So right now our range is still the same. Still negative infinity up to 4.9. And we'll say 4.9 is inclusive. Are these values right here, are the y values between like 5 and 6, are they part of my range? No, that dotted line's not intersecting my graph, right? Is the dotted line now intersecting my graph? At what y value? 6. So the way we do this, the way we show that we have to include 6, because it is a y value of some ordered pair on my graph, but it's only 1 point, right? So we union, and we do that, okay? And that curly brace notation represents a set, and that set only has one value, okay, of 6. So negative infinity to 4.9, along with 6 is basically what that's saying. It is all of my y values. We okay with that kind of understanding? All right. It's just one example, but hopefully that provides us maybe an idea of when we see a picture and they start taking these points and removing them. Okay. A lot of times it's called point removal or point discontinuity. Okay. When they do that, they're doing it to see if we understand the idea, the concept that when I write my D colon parenthesis bracket whatever, when I write that interval, I'm listing all the possible x values that exist if I were able to physically write down the infinite number of ordered pairs. Okay, and then the same thing for my range, but in regards to the y values. Okay, so we have to make sure they're incorporated, even if they're removed off of the curve. Okay. All right. So that being said, let's take and discuss how we would do this stuff algebraically, because the overall goal, guys, is and a great aspect of this course is that graphing stuff's tedious. It can be a pain in the butt. All right? I want to be able to look at that P of X and instantly know what my domain is without having to look at the graph. Does that make sense? Okay? And then if I know what my domain is, then we can use that to judge and determine maybe what my range is later on. Algebraically, finding the range is a lot harder than finding the domain. A lot of times in this class, we're just going to be interested in finding the domain. So we've got some examples here to do this. Okay, we have 5 examples. Couple things that I think we need to write down. Okay. And they come as what we call restrictions. Basically saying that when I deal with anything so far algebraically, whenever a function is presented to me and I want to determine its domain algebraically, this is kind of the process that you go through. Okay? You first assume the domain is all real numbers. Negative infinity to positive infinity, right? Then we go about removing x values that produce undefined y values. And right now we have two situations where that occurs. Okay? So first assume that every time we come across these, so example one, I'm first going to assume negative infinity, positive infinity is my domain. When I get to example two, I assume the same thing. I get to example three, I assume the exact same thing. Okay? And I do that every single time from now to the end of math. Okay? But then we start thinking, okay, after I make that assumption, is it an accurate assumption? I now look at the way my equation is structured, and I start saying, okay, well, there are places that maybe provide an issue. Okay? Think about this for me. Look at example one. If x was negative 5, what do you get underneath the radical? Negative 4. What's the square root of negative 4? What do you guys know that to be? 2i, right? Is 2i on the real number line? No. Okay? And that's what we're trying to do. Domains are finding the real numbers, right? The real numbers that we're allowed to plug in. So 2i, the real numbers that we plug in should provide us real output values. Okay? So the real numbers that we use as x's should give us real numbers as y's, right? Well, I plug in a real number of negative 4 or negative 5, and I get an output of an imaginary value, 2i. That's a problem. Okay? So, why was that a problem? What made that a problem? It was taking the square root of a negative number, right? Okay? So the first issue, the first restriction that we have here is taking square roots. I'm going to write this way, even roots of negative values. Because when I say even roots, if I ask you to take the fourth root of something, is that taking the square root of a square root? So I take square root of like negative 4, I get 2i. Well, when I take the square root of 2i, it's going to be still imaginary. Does that make sense? Okay. So taking even roots of negative numbers provides us issues. And look at number 2 there. What is the value that when we do that division that we have a problem? Okay, so when x is negative 3, we have a problem because we have 1 divided by 0, right? So we don't get a defined value. 1 divided by 0 is undefined. So the second restriction, the second issue is division by 0. Okay? Those are the two things right now that we're going to look every single time at every function we come across to see if they provide us issues with our domain. Okay? And we should then be able to set up our domain as an interval without having to look at a graph. Okay? So we go through these examples. We got, I think we have a little bit more time with the last class had, so we should be able to get through all of these. Okay? So it says f of x equals square root of x plus 1. So we already made the argument that, or you made the argument that if I try negative 5, that's a problem, right? Well, anything more negative, like negative 6 or negative 7 or negative 8, is that going to provide me still the same issue? Right, so negative 6 would be negative 5i underneath there, or sorry, square root of negative 5, which when that comes out, it's going to be, I radical 5, which is a problem, so imaginary. If it's negative 7, it would be negative 6 underneath the root there, so it's still going to be I radical 6, so it's even a bigger problem. Okay, does that kind of make sense? So going to the left of negative 5 is an issue, but let's go to the right. If I plug negative 4 in there, do I still have division, or sorry, do I still have a negative under the root? What about negative 3? What about negative 2? What about negative 1? Okay, negative 1, I get what underneath the root? 0. Can you take square root of 0? Can I take square root of 0? Okay, yes, we can. Because by definition, the square root, we're looking for a number that multiplies 2 times by itself to get the radicand, right? To get 0 in this case. But what number does that? 0. 0 times 0 gives me 0. So I can't take the square root of 0. Okay? So 0, negative 1 works. Does anything to the right of negative 1 work? Does 0 work? Does 1 work? Does 2 work? Okay, and I'm usually using integers here, but does 0.5 work? Okay, does negative 0.999999999 work? Yeah, okay, so it gives me a positive number under that root. So that's what we're looking for. We're trying to make, in order for me to be able to take the square root, this has to be what type of number? Has to be, say it with conviction. What kind of numbers you got to be? Positive. You guys know what conviction is? I'm confident, right? That's going to be positive, right? Okay, so how do I make x plus 1 positive? I do that, right? Does that make sense to everybody? Do you now see the purpose of why we had to talk about solving inequalities first? Because they are a prerequisite to being able to find the domain of a lot of our functions. Okay? So I can solve that. X plus 1 greater than or equal to 0 is going to give me x greater than or equal to negative 1, right? Pretty easy solve, right? Okay. Now somebody's saying, well, why do I got to write that equation out? Because we could do that kind of trial and error thing. X got to be this. No, it didn't work with that value. Try this value. Try that value. That's fine. It works that way. But when our expression x plus 1 gets much more complex, okay, maybe it becomes a polynomial, or maybe it becomes like 1/3 x minus 4/5 or something like that. You don't want to have to do trial and error that way. Does that make sense? Okay. It's simplicity here allowed for the trial and error, but in general, you're going to want to set that inequality up. So if x is greater than or equal to negative 1, we want to convert that to interval notation. So equal to negative 1 would look like that, right? Saying greater than negative 1 would look like that, right? That's the set of values for my domain for this particular function. Hopefully you guys have, from Algebra 2, have a little bit of an understanding of what that graph looks like. Okay, if I look at the square root of x plus 1, it's that curve right there, right? Do you see how the x values, okay, if I go x equals r, create my slider here, do you see at the first domain value that you intersect is negative 1? First x value you come across? And then do we have any x values this way that need to be kicked out? We should have all of them up to infinity, right? They should be all kept in there. And that's what this is saying. It's a pain in the butt a lot of times to draw this graph. Okay? And I'm going to be interested in my domain values a lot. So being able to come up with those domain values quickly and efficiently without having to develop a graph uses this technique. Okay? So that's the idea of taking even roots of negative values. But let's look at example 2. Example 2 here says 1 over 3 plus x. 1 over 3 plus x. This restriction, or this problem that happens with our domain here, is when the denominator turns into what number? 0. So we're going to write this. We're going to say 3 plus x cannot be 0. Okay? When you set up a not equals to equation, essentially, okay, I don't know what to call that, you're going to treat it the same way as an equation. Okay? It's just a visual reminder to tell us that that's the number. When I solve that for x, that's the number that doesn't work. Okay? That's the number that will not make this thing defined as a y value. So x cannot be then negative 3. Does that make sense? Remember what we do at the beginning. We assume that the domain is what? All real numbers. And then we start kicking out values that don't work. Well, what are we seeing here that doesn't work? Negative 3. So our first initial argument is that we should go negative infinity to infinity. And then we got to start kicking things out. Remember how we kick things out? Okay, we're going to put that number that I'm going to kick out there. Union then that number that I'm going to kick out there. And that should effectively give me all my real numbers except for negative 3 in interval notation. Okay. One of the techniques for writing solutions that we haven't talked about because WebAssign doesn't use it very much. We will discuss it at some point. It's called set builder notation. Basically looks like this. I put my curly brace. I write down my x values. That's what I'm going to talk about. And I write this little bar that says such that. And then I say x is an element of all real numbers. meaning that x can be any real number it wants to be, but with semicolon, x cannot be 3. That's maybe a more user-friendly way of writing it. It's a little bit easier to write that. It's to write my assumption first, it's all real numbers, but then start writing down things I have to kick out, right? Does that kind of make sense? That's set builder notation. That's maybe a handwritten way. You can see there's a lot of different ways of actually writing that. I could have written here, all real numbers in words. Okay, so kind of the technology that judges our answers in WebAssign doesn't really set itself up to be able to use set builder notation like that. But that is eventually something that you might see. Okay. Example 3 there. Assume all real numbers, right? Assume all real numbers is my domain, and then I start going through the 2 restrictions that we have: even roots, okay, and division by 0. Do either of those show up there? No. There's no root, there's no division, so do I kick anything out? Nope. Domain, you want to go negative infinity to infinity, or if you want to write it this way, all real numbers, okay? Obviously, what sign is going to make you do the negative infinity, positive infinity, unless directed otherwise. And then, so we should be able to do the next 2 as well. Now, example 4 here, okay? You got roots and you've got division, right? Okay? Think about this. If x was 5, what do you get up top? Square root of 2. Bottom you get 0. Is 5 a problem then? Yes. Yeah. It worked up top, but it doesn't work in the bottom. What if I chose negative 8? Does negative 8 provide me negative root 11 up top? Or root negative 11? Does it give me negative 13 on the bottom? Is it okay on the bottom then? Is it a problem up top? Yeah. So we need, what we're talking about here, when we do our restrictions, it's an and argument. We need x minus 3 to be greater than or equal to 0, don't we? And x minus 5 cannot be 0. So it's going to give me x is greater than or equal to 3. And this is going to give me x cannot be 5, right? But if I use the argument of and, it's going to be the overlap of these essentially. So if x is greater than 3, doesn't it mean this? 3 up to infinity? But we got to have this and, we got to make sure that thing gets kicked out. So we do it that way. Okay? That gives me 3 to infinity, but it removes that one problem of division, right? So in some of our functions, we get the issue where you got even roots and you have division by 0. You got to take care of both of them. The next one's the same thing. Okay, that one there. Okay. What if x is negative 1/2? What do I get right here? If x is negative 1/2, I get 1 divided by square root of 0, right? Well, that's 1 divided by 0. Can I do that? No. So when we deal with square roots, we always say 2x plus 1, the radicand had to be greater than or equal to 0, right? But when that square root comes into the denominator, can it be 0? So that one, that's what you solve for to find your domain. Does that make sense? Okay. That should allow you to get through 2.1 part 2. And obviously that's not due until Friday, but we can talk about that tomorrow. Any questions on that if you have?
Can you assign part 2 yet? Because I didn't see it on.